Hello everyone, welcome back to another video. Today we are going to be going over a couple of different scenarios. The first one is going to be we are going to have a pipe and there's going to be fluid flowing through this pipe, right? And there is going to be a given flow rate for this pipe and we are going to need to determine the head drop at this given flow rate. And then later on we are going to be given a head drop and have to determine the flow rate at that given head drop, right? So our first scenario here, we're going to be given a flow rate and we're going to need to determine the head drop. And right here, we've gone ahead and written out Bernoulli's equation over here. And this is in the head form, which just means that every term was divided by acceleration due to gravity. And pretty much what that does is that puts everything into meters. So we can pretty much determine the flow rate, and we can get that flow rate based on a difference in gravity over here to drive that flow rate, or a difference in pressure over here to drive that flow rate, which we would use a pump to create, or something along the lines of a pump. And so right here, we are going to be given a constant velocity for the water, because there's going to be a constant diameter for the pipe, and we're given a flow rate, and the flow rate's not going to be changing. So we know that the velocity is going to be remaining constant. So we can go ahead and ignore this term right here. That we're not going to have to worry about that at all. And pretty much we are going to need to find the velocity of our fluid, since we're using the flow rate. And in order to do that, we're going to look at our frictional heating over here, our big F. And in a previous video, we determined an expression for that, which is negative 4F. This is the fanning friction factor right here. This is we are using F to represent that. And then we had velocity squared. This is the V we're going to be solving for. That is the velocity of the fluid. And then we had diameter times gravity. We need to include gravity at the bottom over here. Since we divided everything by gravity, we're going to need to divide our expression for the frictional heating by gravity as well. And then this is going to have a 2 out in front. This is going to be our term to represent this over here. And we know that our flow rate is pretty much just going to be equal to the velocity multiplied by the cross-sectional area. So we can say that Q is going to be equal to V times A, right? Our velocity times the cross-sectional area of the pipe. And then we know that the cross-sectional area is going to be equal to pi times the diameter squared over 4. So we can say that Q is equal to V pi d squared over 4. Right here, we are substituting the pi d squared over 4 in for A. And then we can go ahead and do some simple algebra to get V by itself. So the velocity of the fluid within the pipe is going to be equal to 4 times the flow rate, and that is going to be over pi times the diameter of the pipe squared. And then we would go ahead and substitute this in for our V right there. And yeah, this is pretty much going to be the right side of our expression over here. And we have the diameter of our pipe, which we're going to be given, so we're not going to have to worry about that. The acceleration due to gravity, which we're going to have. Pretty much we're going to have everything that we need except for this fanning friction factor right here. So we're going to go ahead and jump into Python now, and we're going to solve an expression for our fanning friction factor right here. Alright, so we have a quick little correction to make. We did forget to include the change in length of our pipe within our equation over here for our frictional heating, so we are going to need to include that. We are going to use delta x to represent that. This is also going to be used to, we are also going to use L to represent this later on, which is going to be the length of the pipe. That is what this delta x is representing. So make sure you guys don't forget about that, and we will go ahead and hop into our Python now. Alright, so over here we have a diagram depicting the friction factor as it changes with the Reynolds number and as it changes over here with our surface roughness over here, or our relative roughness, it looks like it says. So over here, we are pretty much going to be using these Darcy friction factor formulas, specifically the Churchill formulas, to model our friction factor within Python. As you can see, there are lots and lots of different equations that you could use. We are going to go ahead and use the Churchill equations because it's going to allow us to solve for this without having to do any sort of complicated math. We're not going to have to do any nonlinear equations since our friction factor over here is just on the left side and we're just going to have to multiply over. And in a previous video, we discovered that the Fanning friction factor is equal to 16 over the Reynolds number, but over here it is saying that the friction factor is equal to 64 over the Reynolds number, and that's because this diagram right here is using the Darcy friction factor, not the Fanning friction factor. So this Darcy friction factor is actually 4 times larger than the Fanning friction factor, which is why you have this 64 over RE instead of the 16 over RE. And these Churchill equations over here are also using the Darcy friction factor, so we are going to have to multiply this by 4, which means instead of multiplying our right side over here by 8, we are just going to be multiplying it by 2. And pretty much what we're going to be doing now is we're going to be copying these equations into a Python function, which we are going to use to solve for the friction factor based on a Reynolds number that we input into our function, and we are also going to input the roughness of the surface into our function, and that is going to give us our friction factor. So we'll go ahead and do that now. Alright, so we are now over here in Python, and we have gone ahead and written up our function to return our Fanning friction factor. As you can see here, it's pretty much just the exact same thing. We have our theta 1 and theta 2 right here, and then that is going to return the right side of this equation, just multiplied by 2 instead of 8, once again because we are using the Fanning friction factor and not the Darcy friction factor. So that's going to be the only slight difference here. And we'll go ahead and test this out to make sure it's running right. So we'll go ahead over here and take a look at our graph, and say we wanted to find the friction factor when the Reynolds number is 1 million, and then we'll also go when the relative roughness over here is going to be about 0.01. So if we track this down, 0.01 and then 1 million, that is going to give us a friction factor of about 0.38 over here. Excuse me. And this 0.38, that would be if it was using the Darcy friction factor, but since we are going to be using the Fanning friction factor, it's going to be about 1/4 of that. So if our program is running correctly, when we input 1 million for the Reynolds number and 0.01 for the relative roughness, that should give us an answer of about 0.0095. So we'll go ahead and do that. We'll input 1 million for our Reynolds number and then 0.01 for our relative roughness. And as you can see, it's about 9.0095, exactly what we were looking for. So we know our function over here for our friction factor is running swell. So we can go ahead and start writing up our function to give us the head drop. So we will define this and we will call this HD for head drop. Now the values that we are going to be inputting for this is going to be the flow rate of our fluid, and then we are also going to need to input the length of the pipe and also the diameter of the pipe. Those are going to be known, and that is, we are going to have to input that. And then lastly, we are going to need to input the roughness of the pipe, this relative roughness over here. So we will go RR for that. Alright, now our first step within this function is going to be writing up our equation for the velocity of the fluid, which we did earlier on the whiteboard. So we will go ahead and do V is equal to, and then I believe this was 4 times our flow rate. And then this was all over np.pi. And I'm blanking on this. I'm going to go ahead and check on our whiteboard back here. So this was pi multiplied by the diameter squared. And there you have it. That is going to be our equation for our velocity over here. This q is going to be input as well as this diameter. So this is going to give us our equation for the velocity. And then next we are going to need to input our equation for the Reynolds number, which has to do with the density of the fluid as well as the viscosity. So those are both going to be constants that we're going to be given. So we are going to need to include a separate section over here to give us our constants. The first one is going to be our acceleration due to gravity, which is going to be 9.81. And then we're going to have our density that is going to be represented by rho. That is going to be 1,000 or 1 e to the 3. That is representing the density of the fluid. And then we're going to be using mu to represent the viscosity of the fluid. And that is going to be 1 e to the negative 3 right there. We'll go ahead and shift enter all of this. These are going to be all the constants that we're going to be needing to run this function. Alright, and then our Reynolds number equation over here is going to be equal to rho times d times the velocity, and that is all going to be over our viscosity mu. Alright, and then we are going to need to also include our function over here to give us our fanning friction factor. So F is going to be equal to our function that we created earlier, and that is going to be inputted with the Reynolds number that we're solving with this equation, and also our surface roughness that we are inputting into our equation. And then we're simply going to need to return this. Alright, and then for our return over here, this is simply going to be the right side of our equation that we came up with an expression for earlier. And if you remember, we had a 4 in the numerator and a 2 in the denominator, so those are both going to cancel out, and you're just going to be left with a 2 in the numerator. And then we had our fanning friction factor, and then we also had the length, which is the length of the pipe. We had delta x to represent this earlier on in the video. And then we also had our velocity squared. Not sure if this is an uppercase or lowercase, so we'll just go ahead and make it a lowercase again just to be safe. V squared. Alright, and then this is all in the numerator here. And then this was all over our acceleration due to gravity. Once again, so we could get the units into meters and divide everything on both sides of the equation by g. And then this was multiplied by the diameter of the pipe. There we go. That should be our function right there. Invalid syntax. Okay, we had an extra parentheses there. Alright, there we go. Alright, and now we'll go ahead and we'll try out a sample equation. So we'll just go ahead and come up with some random values for this. So we'll say that 0.1 is going to be our flow rate. We'll have the length of 10 meters, a diameter of 0.1, and then for our relative roughness of our pipe here, we'll just say 5e to the negative 3, something random, and we'll see what this gives us. And there you have it. For a pipe that has all of these given variables for its length, diameter, and roughness, when you have a given flow rate of 0.1, that is going to give you a head drop of 25.1822 whatever meters. And there you have it. This is going to give you the head drop required for any given flow rate. And now what we're going to go ahead and do next within our video is we are going to kind of do an inverse function. We are going to be inputting a head drop, and we're going to need to come up with the flow rate for that head drop. So it's going to be a little bit of the opposite of what we just did, and we'll go ahead and jump into that now. Alright, so now we are going to go ahead and come up with a function that is going to give us the flow rate at a given head drop. And we are going to run into some issues, unfortunately, when we try to do this because our velocity kind of pops up all over the place. As you can see, it pops up in our Reynolds number equation, in our velocity equation, and then in our friction equations up here. So that's going to result in some nonlinear equations which aren't going to be very easy to solve. So we are going to have to bring in a root solver in order to solve it for us. And basically what that is going to do is we are going to put in an initial guess for what we think the flow rate is going to be. And then the root solver is going to be changing that initial guess until it finds an answer for the flow rate that is going to give a return function equal to 0, and then that is going to be our answer. So that is what we're going to have to do. So first we'll go ahead and define a flow rate equation. And instead of being given the flow rate, we're going to be given the head drop, which we will just use beta to describe that. And then other than that, it's going to be the same inputs as our head drop function. We're going to have the length of the pipe, the diameter of the pipe, and the roughness of the pipe, like so. Alright, next we're going to define a little vector equation over here. So we'll go x, and then this is going to be, x is going to be equal to 0. Give it an initial array value. Alright, and here, this is where we are going to be returning our equation. And again, we are going to want this to be equal to 0. So basically what we're going to do is we are going to say, we are going to want to return beta, and then we are going to subtract beta minus our actual head drop that we had at the given flow rate. So we'll go ahead and write that out now. Beta minus our head drop, and then this is going to be all the same inputs over here, so we'll go ahead and copy and paste that down here. Paste it up, get these parentheses going, and then we'll need to get some brackets around all of this. So pretty much what this is going to do is we are going to supply an initial guess for what we think the head drop is going to be, and then it is going to go up and down until this head drop value right here that we input is going to be equal to the head drop that we calculated earlier, and then whatever the flow rate is at those given parameters is going to be our answer. But we are going to need to supply an initial guess, and that is going to be a little tricky because, I mean, there's no real common sense way of coming up with a good initial guess. So we are going to have to do a little bit of thinking with that, and we'll go ahead and jump into that now. Alright, so a little bit of a mistake that we need to correct before we move on. We do need to make this Q and then an X over here on the other side so that we get the correct initial value and array going. And yeah, that is just a quick little mistake that we had to correct. Alright, so in order for our root solver to work, we are going to need to supply an initial guess for the flow rate. And we know that the fanning friction number, that has a small range of possible values that it could be. So what that means is we can use an estimated value for the fanning friction factor to go ahead and calculate an initial guess for our flow rate. And we're going to go ahead and hop into doing that now. We know that the head drop is going to be equal to the right side of our equation that we calculated earlier, right? The head drop was simply the left side of the equation, and we know that's going to be equal to the right side, which was our frictional heating over gravity. And we are going to use beta to represent our head drop. This is equal to our frictional heating over gravity. And we're not going to need a negative because we know that if we have a positive head drop, then it is going to be the opposite of whatever the right side of the equation was. And since that already had a negative, that's going to cancel out. So this is going to be positive right here. And then we can go ahead and substitute the expression that we put in for our frictional heating earlier, which was we'll go ahead and use beta once again to represent our head drop. And we had a 4 over a 2, which we will go ahead and cancel out and just leave as a 2 in the numerator right here. And then we had our F, our fanning friction factor, multiplied by our delta X, which is just the length in the pipe, multiplied by the velocity squared in our numerator. And then in our denominator, we had the diameter of the pipe multiplied by the acceleration due to gravity. And there you have it. This was our expression that we used to represent the head drop. And then we are going to go ahead and do some algebra to get this equation in terms of our velocity over here. So we're going to multiply dg over and then divide by 2 times the fanning friction factor divided by also the length of the pipe. And then we're also going to need to square root all of that. So this is going to become v, and this is all going to be the square root of our head drop times the diameter times the acceleration due to gravity, all over 2 times the fanning friction factor multiplied by our delta x right here. All right, this is just the same equation as this, just in terms of our velocity right here. And then now we need to get this in terms of flow, right? Because we want our initial guess for flow rate so that we can plug that in to our root solver and come up with our actual flow rate at the given head drop. So a quick way to do that is just to multiply both sides by the cross-sectional area, right? Because we know that V times A is going to be equal to the flow rate Q. So we'll just go ahead and multiply both sides by A. And we know that A is going to be equal to pi d squared over 4. So we're just going to need to put that in front. So we'll say that Q, right, because we know Q is equal to V times A. So if we multiply both sides by A, this AV is the same thing as this VA, so this just becomes our flow rate right here. We'll go ahead and get some multiplication in there. And so this is going to become Q times pi d squared over 4. And then this square root will remain the same. Beta d gravity over 2 fanning friction times pipe length. And there you have it. This is going to be our expression that we are going to use to come up with our initial guess for the flow rate. And I will go ahead and include that in our Python function now. Alright, so I've gone ahead and written out the equation that we just came up with on the whiteboard for our flow rate guess. And we've also included a guess for our friction factor because once again, there's a small range of numbers that this could possibly be. So we can go ahead and just input something like 0.01 for our fanning friction factor guess. And that is then going to be used down here to give us our flow rate guess. And then we also included our return for the root down here. And we also imported our root from scipy.optimize. And so yeah, this is going to do it for our function right here. All that we have left to do is to go ahead and run all this, make sure it's looking good. Alright, doesn't look like we have any syntax errors or anything like that. So now all we have left to do is to go ahead and check to make sure this is running right. And so in order to check this, we are just going to input over here our head drop that we got for our equation down here to test our head drop function. We're going to head and use that and put that in for our head drop down here. And then we'll go ahead and use the same exact parameters that we did down here. And that should give us this 0.1 flow rate that we inputted, right? If everything is working correctly. So we'll go ahead and use our flow rate equation. We'll copy this head drop that we calculated previously. Paste that on in there. Then we'll go ahead and use these same parameters that we calculated in our sample equation over here. 10.1 and 5e negative 3. And if everything is working correctly, this should give us 0.1 right here. And as you can see, 0.9999, whatever, how many ever nines that is, pretty much 0.1. So it looks like this is working correctly. Everything is working as it should be. So this equation right here will give you the flow rate at an inputted given head drop. And yeah, that is going to do it for today's video. I hope you guys enjoyed. Make sure to like the video if you enjoyed. Subscribe to the channel if you guys want to see more content like this in the future. And yeah, have a good one.